Hello, I'm coming from Virginia Commonwealth University from Safe Lab, supervised by Professor Irfan Ahmed. I'm going to introduce what is ICS and PLC and going deeper into the PLC today. So what are the ICS and PLC? Industrial control systems are essentially the brains behind our critical infrastructure. But not only just critical infrastructure, the escalator that you took today, elevator, everything is controlled by this PLC. It's a small computer that runs a program called control logic. The logic tells the physical machinery what to do. And this programmable logic controller runs that control logic. So we all know that, including recent incidents, we are aware that cyber attacks targeting our critical infrastructure, and it's on the rise. Because critical infrastructure is literally critical, so every enemy wants to destroy this infrastructure and take an advantage. This ICS and the PLC is all communicated in the network, and because network is so important, most existing security research focuses on defending the network. Leaving the memory of the PLC itself, it's remain as blind spot. And this is the gap our research focused on. Let me give you a small example how much this blind spot is neglected. So we all know and we all heard about the incidents in the critical infrastructure. And we all know that, like a smartphone, there is a digital forensic capabilities in the investigation agency. But we never heard of any kinds of digital investigation result report on PLC. They are all analyzing the attack, how it constructed, how it worked, but all of us never had seen any kinds of reports on PLC. So to dive into the PLC's memory, there's a few challenges. First is the fundamental problem. PLC's memory has no rules. Unlike normal computer, PLC memory has no standards, no documentation, no memory layout announcement, no. Every vendor uses their own proprietary format, including their proprietary protocols embedded in the industrial protocols. To make matters worse is the location of the critical data, such as control logic that I mentioned, running the physical process. And those critical data is that we want to target as an attacker, and we want to defend it as a defender. But it changes its location every time we download the control logic to the PLC. So there is no fixed address for control logic, so we need to trace it down every time we download the control logic. This means you're aiming at a moving target in an undocumented environment. The second is interpretation problem. What are we looking at in a PLC's memory? So PLC is working based on a 32-bit, which is 4-byte sequence. And any 4-byte value from 0 to filled with F, it can be a pointer, which means that there's a 32-bit is formed with 30-bit and 2-bit, which means it can control the 4 gigabyte. So even if you find something that, oh, this looks like a pointer value, but you need to understand every random data in a 32-bit sequence can be a pointer. So we need to validate whether this is really a pointer, whether this is really a metadata, or just a data chunk or code data. And finally, we have to deal with the architectural problem in memory and the processor. In memory, we found the RAP phenomena, and in processor, even in the same product family, which is Modicon series in this case, they have a different processor, Renesas and ARM. Let's start with the easy one. Access to the PLC memory through proprietary protocol embedded in the industrial protocol, which is called Modbus. So this UMAS protocol is embedded in the Modbus protocol, which is widely used in industrial control system. And our prior work has already shown that we can dump the memory of the PLC either by using this protocol or in a physical way, which is JTAG. Of course, you can chip off the PLC's chip, but then it's already been crashed physically. So I didn't include that method in here. And for the other challenges, how do we tackle the fundamental challenge? How can you analyze PLC memory when there is no standard layout, no ground truth, and our target data can move when every time program downloaded? So we stopped looking at the fixed location. We focused on inherent characteristics of those metadata and the code data. Something like, if you're looking for somebody, a person, then we are not looking for the physical location of the person. We are looking for their contact, like phone number, contact email address, and all of those metadata, which is going to be the pointer, we're going to have a specific format inside of it. For example, phone number is started with 010, and there's a local code. So like that, we wanted to identify those inherent characteristics of the data itself. And we want to put it into the machine learning model, SVM, and to classify the data based on its structural characteristics. To do this, first we need to implement these 3 types of windows. We were going to pre-process the one huge, in this term, huge is relatively huge compared to the PLC. It's kind of microscope, so 4 GB is huge. Anyway, first we have the primary window, which is typical one, which we set to the 4 bytes, and there's a surrounding windows to compare a small data chunk with its adjacent neighbors. And this we're going to help the model to locate the patterns and the correlations of those data. And finally, the block window allows us to analyze a large region to verify the properties we suspect from the small windows. This block window specifically is also used for those pointers. When we validate the pointer, we need to validate whether the data chunk that pointer is pointing at is valid or not. And in that case, we were going to use the block window too. For more complex challenges, including the pointer issue, how do we distinguish critical metadata, including a pointer from a random 4-byte data? How do we find the execution tree, the true root that controls the execution? And how do we make sense of these replicated data by the RAP phenomena? This grayscaled image is showing the density of the PLC memory data. One of the figures is scaled to show clearly the RAP phenomena is there. As you can see, we can easily observe that there's a repeated pattern. the repeat pattern actually has identical data with each other. And if you modify one, the others also will gonna be affected. This is something that should not happen when, especially for controlling the critical infrastructure, because you cannot adopt some access control to the based on memory space address. So let's go back to the pointer problem first. If any 4-byte value can be a pointer, and these regions are all contain, if these RAP regions are all contain identical data, which one is the real one? Because there should be a real one in one of it. Because PLC, we're gonna use one of it to run the control logic. How can we verify whether which one of it is true? And inside of that true data chunk, which data is the pointer? So we design the features to capture the hierarchy and relationships within the memory. The most important factor to these are depth and in degree. Depth is a measurement of kind of references. We check we do the reference check on the 4-byte value, and we ask how many valid steps can we follow if we treat this data as a pointer. A deep chain suggests it's a significant data. Maybe it's a valuable data. In degree, by the way, in degree measures popularity. How many, we assume all of the data as a pointer. And when we do that, how many pointer we're gonna pointing out in this data chunk. If there's many data pointing out this data chunk, there's a possibility that high chances this will gonna be a valuable data. So with these two reference check feature, we can calculate the relational between the data and effectively distinguish the high value target. So this is the overview of our entire framework. And it all begins with left top PLC memory acquisition, as I mentioned, resolve initial access challenge by using proprietary protocols and JTAG. Once we have the data, it moves into the window-based preprocessing, and then we get to the core of our system, the critical data identification and the machine learning. In the machine learning, there's a multiple features, depth and in degree, as I mentioned, and there's a byte correlation and byte pattern. I'm not gonna explain each of them in a mathematical way. The most important thing is that whether these features are representing different perspectives. Because we design the features, we try to do our best, but there's always chances that we are using the same meaning of the features. So we did the Pearson correlation for evaluating the features. And we deleted all of the features that has more than 0.5. In these correlations, what's important is that there's a too high value in the Pearson correlation. One interesting thing is the depth and byte correlation. Byte correlation is working based on surrounding windows, which we're going to compare the calculated value with the adjacent windows. And how it has a slightly short distance from the other with the depths is because if the pointer value is happen in the memory, it's not exist alone. As you might know, there's a similar case in the file system. When the inode has a pointer value of the file, it's not exist alone. In the table, there's a number of the inode, there's a time, modification time, access time, deletion time, and the size of the file, like that. The pointer is surrounded by the formatted data chunk. So in this case, the depth and integrity is slightly has small distance from the byte correlation. And these are our targets. We tested our method on 3 different PLCs from 2 vendors. We specifically attacked the 2 Schneider models because they use the different instruction set architecture. And the idea here is, even if the instructions are different, the fundamental job of the PLC is remain as same, always. It runs control logic again and again. And to attack the memory, it's kind of straightforward. In case the model found a critical metadata, like pointer, we just change it by a single byte, which hopefully immediate crash the PLC. For code regions, we are copying adjacent instruction sets or non-executable structures and inserting them into the code region, which was enough to corrupt the device's logic. The last one, specifically, boundary read probing, is focused on accessing the precise boundaries between classified memory regions. Because if you run the machine learning, apparently it will going to be divided into a certain block size. In case of M221, it was 1,000 in hex. So why not access those blocks together? As a result, on the M221, our attacks worked very well every single time because we trained the machine learning model on M221, that's obvious. And in case of M241, we found over 280 memory blocks that act like a kill switch. If you poke it properly, then it will gonna die in a one single request. Now, maybe fair question might be raised. Were we just randomly poking the memory until something broke? The answer to this is the critical data region that we classified is less than 1% of the whole memory space size. And when we attack it, we didn't modify the whole data chunk. We were poking 1 byte at a time because maybe sometimes 4 bytes because the window size is full. So we ordered the portion of the critical data that has been classified, and we prioritize the target. So in summary, the targeted data, the size of the targeted data is 1 in a million compared to the total memory space size. To summarize our work, we built an automated framework using machine learning that can find vulnerabilities in PLC memory and identify the critical regions. Next, we prove these threats are severe, and we show that even a simple read request can corrupt the crash to the device, which lead to the CV. Our analysis also uncovers systemic weaknesses exist in the PLC, like in this industrial level device. And there's a phenomena called RAP exist. Actually, this RAP is already been used in other research. So we found RAP phenomena in this research, but while we doing this research, we are not doing only one research, so that one is published faster. So that one exploit RAP region efficiently. finally, I want to briefly cover the ethical perspective of our work. We follow the responsible disclosure process for our findings. We reported, and they patched it. Some are rejected. Some are rejected in a hard to understand way. Some of the answer was like, we are encrypting the network, so why are we concerned about memory? Anyway, and some of the vulnerability that they announced as patched is still exist after the patch, just has a different memory region, which can be identified within minutes. So we were going to report it again, and that's all. Thank you.